So, welcome everybody. Thank you very much for joining me tonight at the British Astronomical Association introductory session on hydrogen line observing of the Milky Way. I need to warn you that this session is being recorded and it will in a few days appear on the British Astronomical Association's YouTube channel. So please be aware of that when you say anything, and please be aware that anything you put in the chat might just appear in that video as well. So I'd recommend that you don't put your emails or other contact details or anything personal in there as well. So the way we're going to organise this session tonight is that I'm going to give a presentation introducing people to hydrogen line radio astronomy of the Milky Way. This is aimed mainly at beginners. I appreciate that not everybody here is a beginner, and some people are just coming for a refresher, and that's absolutely fine. And I'm glad to have the support of people here who do have expertise. But just please be aware that the session is aimed at beginners tonight, and we won't be really discussing too many advanced things within it. And as a result of that, I must also say as well that for those of you who are more knowledgeable, we're aware that there are some more controversial discussions around some elements of hydrogen line astronomy. And some of the things I might say might well be generalizations or things which in other settings are being questioned, whether those sort of ideas should be modified. But bear in mind, this is an introductory session, and I am therefore to some extent presenting things in a simple way. So that presentation is going to take around about 40 minutes, and then after I've finished, Ted Klein, who we've got online here, and who is the author of Easy Radio Astronomy, which is a suite of software which you may be of interest to you if you're considering starting hydrogen line radio astronomy for the first time. He's going to give us a short presentation, about 10 minutes or so, discussing that software with us. And thereafter then we'll have an open discussion time where what happens for the rest of the session will depend on what your needs are and what you'd like to discuss. So you'll be bringing up the topics, and hopefully on this group we have more than enough people with expertise to give at least a stab at some of the answers, or at least direct you to other places where you might be able to get those answers. I'd just like to say that this is my passion, mapping the Milky Way and other aspects of that with hydrogen line, and I'm very grateful to people like Ted and other people like Alex Pettit and Jason Burnfield in Sarah, who have done a wonderful job of mentoring me through this process. And I know that both Ted and I are more than happy to offer help to anybody who wants to get started or needs support. No question is too simple. You don't have to have any knowledge at all of radio astronomy, never mind anything to do with hydrogen line radio astronomy, and you don't need to be an expert in physics or telecommunications or anything like that. The last time I did any physics qualification was an O-level at school. My name is Dr. Andrew Thornett, but that's a medical doctor. It's not in any way anything to do with being a doctor of physics or astronomy or anything like that. So please, and there's no question tonight which is too silly either. Believe me, if you think you're asking a silly question, I've asked it before you. Right, so we'll get started, and hopefully you'll find the evening enjoyable. So we've got about 20 plus people taking part this evening, actually 24 looking at my list here. In addition, I have a number of people who have indicated that they can't make it this evening, but will be looking in online. And if there's anything like the other videos that we have put on the British Astronomical Association website, we tend to find quite large numbers of people viewing those videos. So I'm expecting this to be another popular video for the future. So I'm just going to share my screen. Are you able to let Conrad in there, Andrew?
Just did.
Yeah, brilliant, thank you. So I can leave those things to you. So can you all see that rather bemused looking chap with the glasses next to Lichfield Radio Astronomy or Radio Observatory? Is that visible?
Yeah.
Fantastic. It's a bit embarrassing if you go halfway through a talk to find no one can see it. This is what happened when I asked ChatGTP to draw me a cartoon of my observing station. Of course, my aerials look just like that. Of course they don't, but I do have a log cabin at the bottom of the garden, and that guy in his white lab coat there looks suspiciously like me, including the lack of hair and the glasses and the bemused expression on his face, plus all the wires that look like a real health and safety hazard. What I would say is you don't need any aerials or antenna, whatever word you prefer, to actually be able to do this, or pretty much any amateur radio astronomy project which is done by most beginners to the subject. It's really quite advanced before you get to bigger aerials. I'm British, so I tend to prefer calling them aerials, just say. So when we're talking about hydrogen line radio astronomy of the Milky Way, the hydrogen line, we're talking about 1.42 gigahertz or 1420 megahertz. So this is actually the lower part of the microwave spectrum. Just to put that in context, I've got a book on my shelf from the 1960s on amateur radio astronomy, and this gives a number of projects through chapters, and then right at the end it's got a chapter that it calls Advanced Radio Astronomy, or Radio Astronomy for Advanced Amateurs. And this gives a number of potential projects which it thinks advanced amateurs might do, and then sort of right at the end of that, in less than a page, it talks about mapping recording hydrogen and mapping the Milky Way, and basically writes it off and says, oh, very advanced amateurs are doing this, but you need specialist kit and you need a lot of expertise to do it, and then basically just writes it off and goes on to other things. And I find it amazing that since the 1960s, in such a short period of time, we've gone from only advanced amateurs can do this, who are basically quasi-professional, down to just about anybody, as I'm going to show you, can do this, even as the first project that they ever do in radio astronomy, and without any expertise. And you will see as we go along why that situation has changed, and therefore what's so exciting about the current environment. Right, see if I can get to the next slide. This is, so for those of you not in the UK, this is where I'm located. So UK there up on the right hand side. I'm stuck pretty much just above the middle, give or take about as far away from the sea as you can get, about 300 or 400 miles away. Quite a badly light polluted area, quite a lot of badly radio frequency interference area, but it's still amazing what you can achieve. This is a picture from this last weekend where we had some snow, just looking out in my backyard, so I'm lucky enough to have this back garden, and you can see some of my antennae, we'll call them this time, sticking out there. There's actually 3 of them. You can see that crenulated thing on the left hand side, the dish in the middle, and then a Yagi sticking out just behind it, and that log cabin behind that is my radio shack. So I'm going to start off looking at a few myths that you might want to get rid of if you're new to this subject, as you might think are important. I've already alluded to one, which is that you need an enormous aerial to be able to do any radio astronomy. Like everything else in astronomy, in a sense, bigger is better, but with distinct limitations. Firstly, quite often it's not needed to do a lot, but secondly, bigger brings its own problems, and that thing behind that astronomer there requires an awful lot of mounting, an awful lot of space plus planning permission, and is a right nuisance to try moving around. In fact, if you're a member of the Society of Amateur Radio Astronomy based in the States, then you actually get, as part of your membership, free access to the 20-metre Skynet radio dish at Greenbank. So my friends who do astrophotography, and some of them actually have a telescope that they own between them in Spain, and they're very proud of their remote scope. I say, yeah, that's a great remote scope, but mine's 20 metres in size, and it's located at Greenbank in the US. So if you want a big scope, that's the that would be the thing to do, join SARA. But for the rest of us in our backyards, you can start with something small and very effective. Just another one. I picked them off the internet somewhere, showing that I showed a rather largish sort of aerial. Another one is the idea that you need to fight with equipment. Now, I started doing radio astronomy around about 15 years ago, and that's where I first met Ian here, who's also on this call, from Tamworth. And at that time, indeed, you did have to do a certain amount of fighting with equipment. My first radio was an ICOM R7000, which was supposed to be the bee's knees for amateur radio astronomers in those days, and it was reasonably big. It cost me a couple of £100 off YouTube just for the receiver, and it was nowhere near as good as things that you can buy these days that are much cheaper. In fact, a small software-defined radio these days has much lower noise levels, is much simpler to use, much lower power, and the data is much easier to manipulate. And you don't need to muck around with it like this guy is having to do here. In this graphic, it says you need to personally monitor your telescope day and night. Well, in fact, for most radio astronomy projects, that is correct in a way. The radio telescope does need to collect data all day and night, but the days when Jocelyn Bell had to look through miles of tape to try and find her WOW signal have gone. We have computers that do things for us, and that includes collecting the data. So now you set it up running, and then you go off and do your other bits of life, and then you come back and you process it with something like TED's wonderful software, and lo and behold, your issue is not collecting the data or even processing it, but it is trying to understand it at the end, where it might be a bit confusing. TED's software churns out about 250 graphs and becomes, what on earth do these graphs mean? But I do want to start, perhaps, I know many of us here have been doing radio astronomy for a long period of time, but I don't know everybody personally, and I don't want to presume a certain level of knowledge for people who haven't got it. And again, there's the people who might be looking in online who may not have done any of this stuff before. So this slide is worth having just to remind you. So this shows the radio window, as it's called. Basically, it shows a spectrum of light and shows which parts of that light or electromagnetic spectrum reach the ground. And that is demonstrated in the graphic at the top, by which parts of the line get down to 0%. Now, the thing to bear in mind is that the bit that shows the red, white and blue, etc., around about 1 micrometer, that's visible light. And apart from that, the only good area of the electromagnetic spectrum that reaches the ground is our radio waves, which, as you can see, are just under about 10 centimeters, going up to just above 10 meters there. So there's a couple of things that stand out about that. If you can't look at that area of the sky, then you're missing out on quite a lot of data that's coming to the Earth. But secondly, it's a much wider part of the electromagnetic spectrum than the optical spectrum covers. So therefore, if all you're looking at the sky is with an optical telescope or with your camera, then you're missing out on quite a lot of what's available to you. That wide range of the radio window covers a whole range of different experiments, from things that look at solar flares hitting the atmosphere, to detecting meteors as they come into the atmosphere, to detecting signals coming out of Jupiter, to a whole variety of other things, and including what we're looking at tonight, which is the radio wavelength of hydrogen. To me, I think that detecting hydrogen and therefore mapping the Milky Way is one of the most incredible things that you can do. I've so far mentioned mapping the Milky Way. Other things that you can do include weighing our galaxy, that's our personal galaxy, Milky Way. I've said demonstrating dark matter. Just before we started here, Andrew here did jokingly pull my leg on that, and he's quite right. Of course, we can't demonstrate dark matter because dark matter's dark, you can't see it. But what we can see is the smoking gun for dark matter. It's the physics that have caused astronomers to conclude that that exists. So if you don't believe in dark matter, that's absolutely fine. There are other explanations, such as modified Newtonian dynamics, that I have to admit. But I still think it's incredible that from our own backyards we can demonstrate the same physics that have caused this whole issue to come to light. and led to such controversy. As I say, back in the 1960s, this was a very difficult project, and I think the best way for me to describe this, I'll explain it to you perhaps, is to say that as little as 10 years or so ago, I was involved in a project with a chap from the BAA called Brian Coleman, who some of you will know. And Brian has a 3-metre telescope, and at that time he wanted to set up a project where people could start to collect data from the Milky Way using his 3-metre telescope and start a process of trying to map out the Milky Way. But to do that at that time, he had to move his telescope to point at a particular spot. Then he would collect data for a while, and then one of us in the project would analyse the data, or scientific terms it's called reducing the data, and we'd end up with the data for 1 pixel. It would take a couple of hours for us to do that. It was done on Excel spreadsheets, basically little more than a pen and paper job. That's what it took. Now TED software will do that all for you while you go off to make a cup of tea, and you come back and even present you with the map at the end. Quite remarkable. The equipment at the time, as you see, he was using a 3-metre telescope. He would have been using what would have been at the time quite expensive receivers and handmade filters and amplifiers. But now all this kit is now starting to be available out of the box from commercial firms who are seeing that there is a demand for hydrogen line observing hardware, and they're selling it on people like Amazon, eBay and other famous online sites. And in particular, one device called Newelec, Sawbird H1, has pretty well revolutionised the whole situation, and we'll talk about that in a second or two. In particular, these things called software-defined radios, and this kit is so good these days that it will even work with a 70-centimetre dish. To make the situation even easier, and this is what I started off doing, SARA, the Society of Amateur Radio Astronomers that I talked to you a minute ago about, they've actually set it all together as a project called Scope in a Box. And if you're in America, you can pay your $350 and they will send you all the kit that you require to put it together, which they source from Amazon there and send out. They don't send it out outside of the States, but they will happily provide a list of all the components that are required for you to source them yourself. And I can also provide that to anybody that wants it. In fact, it is extremely easy to source all of those components in the UK or in Europe, and I would say there are better components than the original Scope in the Box hardware list. The total cost of doing a project like this, initial setup, around about £200, $250 or €250, something like that. Now, why would we want to do all of this? If you take a camera from your backyard and you take a picture of the night sky, it doesn't matter how good your picture is. At the end of the day, you're just looking out from the Earth and seeing what hits the camera first, and it's very difficult to see behind that. Yes, with something like the James Webb telescope, you can peer through the dust and see the stars behind the dust and get a bit further. But in order to get any further idea than that, you would need to get very precise measurements of movement of those stars, and the Gaia satellite, the European Space Agency's Gaia satellite, did just that for about 2 billion stars. But it also cost an appropriately large price tag, not something that we can do. How do we know that there are spiral arms in the Milky Way? How can we basically get a picture of the Milky Way as if we were outside it, looking down from the top? And this is where radio comes in. It was due to radio that the Milky Way structure was able to be determined, and that is something that we can also do ourselves. And we can achieve a picture, which is shown in that graphic, as if we were outside, above the centre of the Milky Way, looking down on it, and seeing the plane of the Milky Way from that sort of coronal direction. Here's another graphic produced from professional data, which shows the names of the arms of the Milky Way. And for me, I wondered for ages how professionals knew that these arms existed, and whether perhaps they were imagining them without any significant evidence. So to show how this is done, I need to just introduce the concept of Doppler shift. Again, I know that most people will already know about this, but just in case, so there might be somebody who doesn't, I'm going to just go over it again. So in this particular graphic, we've got a car, and at the top, the car is stationary, and so sound waves, when the car's engine revs, go out in both directions, as you might guess, in all directions. And this, imagining some of them going out the front towards this observer, and some of them going out in the back in the other direction towards another observer. Now clearly they're going to hear the same sound, but if you're as in the situation at the bottom where the car is travelling at some speed towards you, then you will hear a higher tone than if you are behind the car, where you'll hear a lower tone. This is because, as you can see from the graphic, sound gets compressed in front of the car, which effectively reduces the wavelength or increases the frequency, and it gets dragged out behind the car, which has the opposite effect. So I want you to imagine the last time you stood at a train platform and a fast train went past, and you might remember that as the train came towards you, it's like going and the sound goes up, and then as soon as it goes past you, the sound suddenly drops. And that's that same process of what we call Doppler shifting of the signals. That's with sound. But if you've got light, this is where you get the famous red shift and blue shift. So what you see on the screen are the equivalent of Fraunhofer lines for hydrogen, which you might see in the spectrum of the sun, perhaps at the top. But if you had another cloud of dust or gas, and if that was moving away from us, then those same lines for hydrogen get shifted towards the higher wavelength end of the spectrum. It gets more red in colour, and likewise, if it's moving away from us. Sorry, other way around. Bear with me. Yeah, moving away from us, it gets red shifted. If it's moving towards us, then it gets moves towards the blue side, as you can see from those lines on the graphic. Now, I mentioned that we have some hardware available now that didn't used to be available, which has revolutionised everything together with the software. I'm having some difficulty getting my computer to move slides. Here we are. I mentioned the green back dish for those who are members of SARA. Right, more practically, for your backyard, this is the sort of dish that you might be using if you want to get an off-the-shelf dish. You've got choices. You can there are now some that you can buy off the shelf, or alternatively, you can make antennae for yourself, aerials for yourself. This one's a Newelec grid antenna. It's about 100 centimetres wide, about 60 centimetres on the short axis. And it gives you an idea of the basic setup of one of these dishes. You get the dish, and then you get a boom in the middle, and you get some sort of waveguide at the end. Before you go out and buy this particular one, there is Alex Pettit on the SARA mailing list has pointed out there is an issue with the length of the boom on this, so have a chat to one of us before you buy something like this. There are other options. Hydrogen itself in 1951 was first demonstrated using a horn. This is an example of a homemade horn, or what is that? Example of a homemade SETI horn of plenty, as it is called. SETI have put designs for this online. And so this is, as you can see, is a device that likewise collects radio waves through the open aperture and funnels it down at the end until the little box at the end, where it then collects it on what's called a waveguide. There's the original Horn of Plenty, or at least I think it might be a copy of it, with Harold Ewan, who was one of the original observers that discovered hydrogen in the Milky Way. It's worth mentioning this one. So this is a crowd-funded project which is currently available, where they produce something called the Discovery Dish and H-line feed. This one works incredibly well. It uses a 70 centimetre dish and comes with all the kit that you need. Basically, you take this, you plug the end of the cable into a software-defined radio on your computer, and you're well away. So that's just another off-the-shelf option that's available. That one costs around about £350, about $400 or €400 if you want to buy it. But, as I said, people do make their own, and the Square Kilometre Array has got an outreach team which goes around to schools helping them to make hydrogen line telescopes in the classroom in a single session. Here's some example of the types of telescopes they make. As you can see, made with cardboard, silver foil, old umbrellas and the works. We had a conference here in the UK called the European Conference of Amateur Radio Astronomy, or UCARA, which was in September, and one of their members, a Japanese chap who was an excellent speaker and quite hilarious, was showing us how to make these things out of balloons and bird baths. But the bottom line is you can make a hydrogen line radio telescope out of virtually anything as long as it's got conductive material on it. Clearly, if it's made of cardboard, it's not going to be very robust. But if you were just trying to demonstrate that you could pick up hydrogen, one of these works very well. If you want to take it further and leave it out for a long period of time to do things like mapping the Milky Way, then you'd need something that was made of a more robust material. Having said that, you can make a hydrogen line telescope that works out of a coffee can, and this is an example of one that I've made. They're being tested in my backyard. If you wonder what's over the front of it, it's some cling film, see-through kitchen film, just to stop the rain from going into it. But that did successfully pick up hydrogen. I admit it wasn't terribly effective, hasn't got a very big aperture, but it did the job. So I haven't thrown it away. I turned it round the other direction and used it as the waveguide for my dish instead. Much more effective. And then you get posher designs that people have used to make their own dishes. So this is something called a geodesic design, which is often used to make domes in gardens and things, but can be used for making dishes. And this is where you can use the natural way that rods and wooden beams curve to actually get close to a parabolic. And with a bit of modification, you can achieve that parabolic shape. Just a bit more about that. Myself, I use one of these, which I was given, got me started. I wouldn't suggest going out to try to buy one of these. I've never actually seen one ever anywhere else. It's an ex-military dipole array. Those little rods on it are dipole aerials. As you can see, 16 of them on there, on a corner reflector background. It isn't anything better than the other dishes. It's 86 centimetres by 86 centimetres. It performs about the same as a metre dish. It has two unique special features. One is it's very robust, which is great when you've got an idiot like me looking after it. And the second thing is that when I first set up one of these telescopes, my wife didn't want a dish in the garden, and she felt this one looked more like a barbecue and was more ready to accept it. So that was quite an important reason for having it. But the main reason for showing this picture is not to talk about that particular antenna. It's to show you two other things. Firstly, my computer and amplifier, etc., is in that black box under the computer. So I just use these boxes. You can buy them for about £20 downtown from a range of sellers. Easy to get hold of, quite convenient, and keep stuff watertight outside. But more important is the mount that I've got it on, which, as you can see, is just a load of bits of wood nailed and screwed together. And it literally is a load of bits of wood nailed and screwed together from our local hardware store, which has a cutting room. And when people have bought their wood, they pay a bit extra to get the wood cut. And then what's discarded in the corner, of course, has already been paid for. And I go along and pick up an armful of this stuff, and I go to the front desk and they charge me £3 or £4 and I walk away with it. It's obviously irregularly shaped, but it does the trick. I nail and screw it together. All that really matters is that I have a robust mount. These days you can download compasses and also digital inclinometers. A digital inclinometer is a device for, if you point your device, it'll tell you what the angle is with that relative to ground, i.e. what the altitude is that it's pointing up at. And it'll do that with great accuracy. And those are the two bits of information that we require to plug into TED's software or into something like SDR Sharp. So I can use those to tell me exactly which direction my telescope is pointing in. It just needs to be robust and not move. You can just about see at the top the two little bits of wood that are, at that particular stage weren't painted, and just on the outside of them are two battens that are going down at an angle. And those two battens you can't see from here, but they have holes drilled in them. And by using those holes, I can change, there's another bolt sticking out at the bottom, and I can change which hole that they stick into, and as a result of that I can change the elevation of the ptarmigan array there, i.e. where it's pointing at in the sky. And I can use my digital inclinometer to tell me what angle it's pointing up at. And those are the only thing I need to be able to do with this. If I want a more sort of detailed look at the sky, I drill more holes in the batten so I can move it to more subtle changes in altitude. The way that the software works these days, you don't need to be able to move your telescope around and point at different parts of the sky. Basically, you point at a single part of the sky and it keeps pointing there for the next 24 hours or so, and the software will take apart the data that comes through and create basically a whole database of data at different points in the sky as the Earth rotates, and give you the entire 360 degrees. And then you change the altitude, so you get the next line up, and they change it again, next line up, until you cover as much of the sky as you're able to do so. Also, if you're using something like TED software, you actually can point it in any direction you want. We tend to point it about 180 degrees, but it doesn't matter if it's slightly off from that. And it happens that this is pointed at 167 degrees, and the reason for that is that's neater on my patio. It follows the lines of the patio. That's the only reason. Right, so in the top left of this picture here, we've got one of these software-defined radios that I've been mentioning several times. And this is an example of one of the RTL SDR blog devices. This is a rather older version of it. You might be able to see on there, if you can, you've got good resolution on your monitor, it says DVB-T plus DAB plus FM plus SDR. And that tells you a lot where these things have come from. These were devices that were originally developed to allow people to basically turn their old analog TVs into digital TVs. You could plug it in and use it that way. So, or turn their computers into a TV. They're very cheap. These cost about £30 or £40, or the latest version about £50 off Amazon or the similar websites. They come in different varieties. You can buy a non-branded version for about £20 odd if you want, and they'll easily cover the wavelength that we're looking at. On the right hand side, you've got a Newelex Sawbird H1LNA. I've got to say, there are, for all of these things, there are alternatives. You don't have to have exactly these ones, so you may well already have one that is used for other purposes, that's a slightly different brand that could be used. So check with that first, or if you're going to use TED software, check that his software will use it. So I think it's worth talking about the Sawbird a little bit, because it explains some of the issues that there are in trying to detect hydrogen and measure it, and also explains why it was such a difficult task back in the 1960s and required an advanced amateur. And why Brian had to personally make amplifiers and filters to get his system to work. And this was before things like the Sawbird were available. So firstly, we need to state that microwave signals have a problem in being transmitted down a coaxial cable, which is that they tend to suffer quite a bit of loss. So we tend to measure strength of signals in decibels, which you will have heard of. But if I say to you that that a signal has degraded by 2 decibels, that doesn't sound very much. until you realise that 2 decibels or so is around about half the signal strength. So if you've got your nice big dish out there and you end up losing the equivalent of half the aperture of the dish just by going down the cable, that's a massive difference. And the difference is enough to probably mean that you won't see anything at all when you try to collect your signal the other side. So the first thing that we want to do is amplify the signal. Well, sorry, I should say, even if you use high quality coax that's designed for this wavelength, you still see some loss of signal. So you're probably still going to see, it'll be less than 1 decibel, but you might well be seeing something like 0.6 decibels to 0.8 decibels, depending on which type of coax you use, unless you get extremely expensive coax, where you might get down to about 0.4 decibels. But you'll still be seeing a significant loss. So inside this Sawbird device, there are 3 items. It starts off with an amplifier, that's followed by a filter, and that's followed by another amplifier. So in reverse order, the last amplifier amplifies the signal so that when it goes down the cable that you're going to use, it compensates for the loss that's going to go down the cable. The filter in the middle takes away out-of-band signals, because even though your computer and SDR will be tuning into a particular signal, if there are some strong signals close by in the radio spectrum, they can still leak across and cause problems with your signal. So there's a filter in the middle. The problem is the filter that's in the middle of this device called SAW filter itself causes some loss of signal. So the first amplifier is a sort of small amplifier which is designed to amplify the signal enough to compensate for the loss that you're going to get in the filter. Then you have the filter, and then you have another amplifier which is going to compensate for the loss that you get in the cable. And now you can see why this gets all rather complicated. It also explains why the fact that you can buy this device and just forget about it, you don't even need to understand a word that I've just said to you. It just basically means you get one of these and shove it just behind your dish or your horn or whatever it is that you're using to collect your data, as close to the feed of that horn or dish or whatever as you can, and then your cable comes out the other end and you can forget about it. Works very well. Then this works so effectively that in terms of the coaxial cable that you need, in fact RG6 cable works very well, and RG6 cable is that coax that if you've had a sky dish outside your house or a satellite dish on your house, it is a type of cable, that cheap cable that they run around your house to take the satellite signal in. So you can use one of those cheap cables. It does need to be a cable which is rated for the frequency. So if you're an amateur radio individual, you may have loads of RG58 hanging around. I'm afraid RG58 cable's no good, because that causes too much loss because it's not rated at this level. So you need to get one of these SDRs, and you need to get an amplifier and filter, which either a Sawbird or something else that does the same trick. Here's an example of another software-defined radio. Just show there are different choices, and here's a whole variety of other ones, different prices, different sizes, different specifications. The RTL SDR is probably one of the cheaper ones, and also works incredibly easily with this project, which is what we tend to recommend it. And just I picked it up a price just for your idea what to at this moment in time. That's about £41 there. And likewise here, one of those new Alex, I got £42.95 at the moment coming up. And if you did want to get that new Alex mesh antenna, but as I say, speak to us first before you bought one of these, because of some issues with it. That's currently £142.55. And you'd also need some sort of mount to put it on. You could use a pole, or you could just buy one of these satellite tripods, which is what's currently recommended in the Scope in the Box project. And again, sort of £38. Let's ignore that. Okay. Right. So that's the hardware. And I'm going to go and have a little quick look at the software that you would use with this. In terms of the computer that you've got, what's great about most things in amateur radio astronomy is that just about any old computer that will run Windows 10 or 11 or Linux is good enough. One of the other things that I do, sorry, I've got to take a drink, excuse me. I don't know, my mouth's very dry. One of the other things I do is solar astrophotography, and if I take my kit outside and do a run for 3 or 4 hours, especially if I'm trying to video a prominence on the sun, I'll stick 160 gigabytes on the SSD. I'll need a computer with a high processor speed. I'll need a lot of RAM so I can run a RAM disk, because it's very likely that the data will be coming in faster than it can be stuck on the SSD. And then I'll need a very powerful computer to process the results. That's in solar astrophotography or planetary astrophotography. It is not in radio astronomy, where most of the time you don't really need a graphics card, and most old computers, as I say, will do the trick. So here's the time to dust out that computer you've got up in the attic that you wanted to go and take down the tip and throw away but haven't got round to it, or just put a request around the area if anybody else has got one they want to get rid of, and just use that. All it needs to do is to be able to be left on 24 hours a day. You don't need to leave the screen on 24 hours a day, I just mentioned. So regarding to software, we've got a couple of choices which are commonly used. So first of all, I'm going to mention a piece of software called SDR Sharp. So SDR Sharp is a commercial piece of software, at least it was produced by a commercial firm, though the software itself is free. And SDR Sharp has to be used in conjunction with a plugin. If you use something like Adobe Photoshop or Affinity Photo or anything like that, you'll be used to plugins, which are extra bits of software that can add to an existing program and increase its functionality. In this particular case, IF Average plugin allows you to collect data over a prolonged period of time and integrate it to produce a single sample, which is required because hydrogen is a very weak signal. And that's free to download online, or we can push you towards where to get hold of it. And on this diagram here, we actually have the signal of hydrogen being shown, picked up with SDR Sharp. And you might think that hydrogen is going to appear on the screen as a single peak. After all, hydrogen's 1420.40 megahertz, isn't it? And if you look at the 1420 megahertz, which you can see on the bottom on the x-axis on the left-hand side graph, what strikes you is there's nothing there. Now, when I first saw that, I got to admit, I thought that my kit wasn't working properly. Now, I had seen in the Scope of the Box manual a picture that showed what it's supposed to look like, and I looked on this screen and I thought, well, it's supposed to look like what I can see here between 1419.2 and 1419.8. And if you look at that, you can see there's a peak on the right hand side, and there's a sort of there's a broader lower hump on the left hand side. Take it from me that all of that is hydrogen. And firstly, it's spread out, it isn't a single spike, and it's not at 1420 megahertz. Well, I picked that up one day. On another day I was looking, and it was to the right of the 1420 megahertz, and now I was going bonkers, thinking my stuff was my kit was really not working at all, and I really couldn't fathom what was wrong with these things. I now realise that there was nothing wrong with my kit at all. It was working perfectly fine. This is all to do with Doppler shift, which is what I mentioned before. In this particular case, we've got Doppler shift in the signal itself, which has been spread out between 1419.2 and to 1419.6. Is it 6 or 0.8? 0.6, I think, or 0.8. I can't see properly on my screen. And that's because the hydrogen that we're looking at, we've got hydrogen in different parts of the Milky Way, and that hydrogen is moving at different velocities or different speeds. And that data on velocity or speed that's contained within there is what Ted uses to create his maps in easy radio astronomy. The second thing we've got is that the whole lot of that data is lower than 1420, because the part of the Milky Way that I'm looking at here is moving towards us. If on the other side, it would be moving away from us. And again, that's to do with Doppler shifts. It depended on which way I was pointing my telescope at the time. On the right-hand side, we've got another graph, and this one shows a couple of peaks. And this is actually the graph of detection of the hydrogen, or at least the whole spectrum, before the IF average plugin is applied. So this is sort of more instantaneous one. And the first thing you see is these various peaks, and those, or at least all those humps. And those humps are actually representing the response of the software-defined radio to different frequencies. You see, it's not the same throughout. So this is why you need some sort of reference to go on, because I haven't mentioned that on the left-hand side, this has also been corrected using a reference frame. And that reference frame gives the response of the software-defined radio without the hydrogen. And we can deduct that and get a flatter baseline and show up the hydrogen more effectively. There's also got the integration there on the left-hand side. This is a bit like the similar thing that you do in astrophotography, where you get your dark frames and your flat frames and your bias frames and all that sort of stuff. Okay, so this is just, again, just more details showing the same thing. So, the next piece of software I'm going to talk about is Easy Radio Astronomy, which is Ted's radio astronomy here. I'm not going to give too much information on it because Ted's going to give us a lot more later on. That just gives you a link. It's on Windows and Linux. Really, this is just a picture, just showing that data being collected in Easy Radio Astronomy. And again, this is a corrected sample, showing a slightly different type of graph from the previous one, which is why it looks different. But again, you can see in this particular case, we are hitting closer to 1420, but we also have the Doppler shift showing up there. Again, showing hydrogen, this time with two peaks, probably from two different arms of the Milky Way. Now, moving on now, Alex Pettit is a member of Zara, and he's produced his own software called H-Line 3D, which allows you to do some more detailed, sort of accurate analysis of the performance of your dish, if you want to look at it in detail, and links through to a process of starting to turn some of this data into three-dimensional work, which Ted and I then took forward, and you're going to see in a minute or two with what we did with it. But you can see on the right-hand side that he's presenting some of those that data as it goes through the Milky Way in those peaks, which are the power peaks, presented in 3D format to make it more visual. Right, and he's just some more data there on him, some evaluations. All right. So, I quite like this graphic because it gives some idea of what needs to happen in order to convert the hydrogen line data that we're collecting into those maps that, that Ted produces, and other graphs that he's producing there. So we're located on this sort of scale, the same place as the sun there, and the black line that says line of sight is our telescope is looking out in that direction. Now, it's not exactly true because clouds of hydrogen move at different speeds, but give or take, at a set distance away from the galaxy centre, hydrogen's moving at roughly the same speed around the galaxy. So galaxy centre. So from this, from the information of speed, we can roughly calculate how far we are away from the centre of the galaxy, and that helps with the mapping exercise. You can see there that I've given arrows to indicate in which direction this sort of hydrogen will be moving. Our telescope picks up the component of that movement that's along the same line as that black line that says line of sight. So what this means is that both A and C look the same to our telescope. That's why they're both in pink, even though, as you can see, they're in different parts of the galaxy and moving in different directions, because the component of the movement that's going towards the line, in the line of sight, or at least towards us more accurately, is the same. Likewise, E there, which looks slightly different on both sides, D, forgive me, looks as if it is moving slightly away from us on the left hand side, I should say, but on the right hand side is presented as moving horizontally relative to us, and therefore, as far as we're concerned in our line of sight, is actually not moving at all, because we're not picking up the horizontal component. So you can see now where Ted's clever logic engine in his software comes in and achieves quite a lot, and you can see also why back in the 1960s and even in the time of Brian Coleman's H-log project 10-15 years ago, there was quite a lot of analysis and clever thinking required to turn this data into a hydrogen line map. Now you don't need to bother to do it, the software will do it all for you. So you might be interested to see what sort of results you get out of this. So this is from a ptarmigan array there, and so the background on this map is professional data, and my data are the green lines that are coming across here. And you can see that we are successfully picking up the Milky Way, because we get the bumps up each time we hit the Milky Way on both sides, and each of these green lines represents a drift scan. I started off when I began this doing them for about 2 days at a time, just to make sure I covered 24 hours. Then later I turned it to a week, which improves the signal to noise ratio somewhat, improves the maps. I finished that map, and I'm now repeating the map, but this time with a month on each of the elevations, i.e. just a month on a single line, and that does seem to be producing better quality maps. So all the more reason why not to rush to keep changing your elevations too fast. I've now got my one map at the moment has 200,000 hours of data in it. So it does sort of somewhat beat the astrophotography, photos at 30 hours at a time. So it's me showing off a bit there. Anyway, you can see the range of elevations able to achieve. This, I can go up to right up to 90 at the top, but I can't go much further than the -15 that's there. So you are limited by where you are on the planet as to how much of the sky you can cover. And this is my map of the Milky Way with 2,000 hours, 500,000 observations is what I've achieved. You can see managed to get a good picture of the Sagittarius arm there, with the Perseus arm and a little bit of the outer arm coming out. And I can tell you that we've also got a couple of small inner arms inside the Sagittarius there, or parts of arms, which you'll see in a minute or two on the 3D plots. This also shows another limitation from our backyard, which is due to both limitations of the software and the mathematics, and also our location on the planet. We can only really get around about 90 degrees of the map. But I am at least demonstrating the spiral arms of the Milky Way. Now this graphic is a Commons graphic coming off Wikipedia, and I'm going to this is really just to give you an idea about I'm going to call it dark matter. It's the smoking gun for dark matter. It's the data that needs some explanation, which many people have used dark matter as the explanation for. So really it's showing that difference between the rotational velocity of the galaxy as we would expect it to be from what we actually find it to be, that's creating all the problem. So first of all, just to run the video first. Oops. Why am I not running? Oh dear. Here we are. So what I want you to notice is that the inner part of the galaxy is moving at the same speed, but the outside of the galaxy is moving more slowly on the left hand side than it is on the right hand side. Okay, and the reason for that is that is demonstrated by these graphs here. So on the left-hand side, we have a graph what we call Keplerian rotational velocity, which is where you get it very fast in the centre and it drops off exponentially towards the outside. On the right-hand side is what we actually see near enough, which is that the velocity stays approximately the same across the span of the galaxy. And the dark matter explanation, if you believe it, is that the reason this occurs is because there's a lot more matter on the outside somewhere, which is stopping it from slowing down on the inside. Modified Newtonian dynamics gives an alternative explanation of change in gravity at long distances. I need to mention that. So now we're going to compare, on the left-hand side, this is Keplerian data for the planets of our solar system, which has come off Wikipedia, which is Ted has put together to make a graph for us. And this shows, as expected, in fact that's what Kepler based his rules on, that Mercury is the fastest, closest to the Sun, rotational speed, and as we get further out, all the way in this case to Pluto, it drops off exponentially, just as we would expect, not least of all because that's where he developed his rules from. But on the right-hand side, it's from my data from my radio telescope, and I'm very proud of this. So this is in kiloparsecs. So a parsec's what, 3 point something, isn't it? 3 point something light years. So from 4 kiloparsecs, 4,000 parsecs, out to about 8,000 parsecs, which is where the Sun is, so we can't go any further because the Sun's there. And you can see that my graph shows something much more akin to a flat line than the Keplerian rotation on the left-hand side. So that's smoking gun for dark matter, or whatever else you think is the explanation. I just find it amazing that I can demonstrate that from my backyard. And here's something else which I think is pretty neat. According to Wikipedia, the Sun should be travelling at 220 kilometres per second around the Milky Way. My maximum is 243, so it looks like I'm about 10% over. Well, that's not too bad, you know, just from my backyard. I'm not doing a scientific experiment. I think 10% were quite reasonable. But then I did a bit of research online, and I came up with this graph on the left-hand side from the Very Large Baseliner Interferometer, and you can see there that shows a graph showing velocity of the Milky Way, which, lo and behold, seems to show a velocity which is much more akin to my velocity on the right-hand side, which is just a replica of the previous graph. So I just wonder whether actually I'm got a better value than Wikipedia did. I don't know. And then I mentioned weighing the Milky Way, so here we are. This is me weighing the Milky Way from 1 kiloparsec out to 8 kiloparsecs. This is quite a robust bit of that comes out of your data. Very easy to produce this, and a kind of neat graph coming out there, which I'm quite proud of again. So as I say, Ted Klein that is, and I took this a step further, and we developed a process where we used a piece of software called Rinnen 3D to take the Ezra data and turn it into 3D plots. Ted produced some enhancements in Ezra to produce the type of data that can be taken into Rinnen 3D. And so these are my 3D plots of the arms of the Milky Way that have been picked up at 90 degrees with the Sun, or us, located as indicated from the orange circle. And you can see we've got those two arms showing up very well in 3 dimensions. A few more plots of the same thing from different directions. And this is the graph that shows the 2 extra small inner arms that I was able to pick up on that 3D plot, which I thought was pretty neat. And I'm pretty much finished now, but just a little bit more about my setup. So you can use just about any old computer to run these experiments. Quite a lot of people use Raspberry Pis and Arduinos, those sort of things. Personally, I'm now trying to learn a bit of Linux, because you get to a stage eventually where Linux is worth learning, but way beyond where we are today. But I get these old mini PCs, i5 mini PCs, which you can buy off eBay here in the UK for around about £50 or £60. And because I do quite a lot of radio astronomy, I run one on each computer, which means they don't conflict with each other. So that's just one particular idea, or any old computer, as I say, that somebody might give you. And that's that box that I showed that was underneath the ptarmigan array. The eagle-eyed of you will see the gold device at the top on the left-hand side. That was an extra amplifier, which at the beginning I thought I needed, but just to say that's not used anymore. That's gone. You don't need it. Sawbird's absolutely fine. In this particular case, the sawbird is located here, which is unusual, and that's just to do with the cable coming out of the aerial, and the fact that I've got everything so close to the aerial. Normally, I would say you put the sawbird as close to the aerial as you possibly can, with a little cable between the aerial and it as possible. In this particular case, I ran into another problem, which is why you see a small dehumidifier and some bricks within the box. And that is the first day I set this all up and ran it outside. It was in winter. I came back the next day to find a puddle in the bottom of the box. And it wasn't because there was any leak, it was simply because dew was condensing on the inside of the box and running down it. So that's a little caravan dehumidifier, which quite successfully keeps the box empty of dew now. That laptop is just one somebody that gave me. It is an old laptop. It's nothing special. Oh, that's just a picture where of my shack with all my sort of stuff in at the moment. Right, just for anybody who wants to take this a bit further, just to say that Ted and I have been looking at ways that you can do extra things with easy radio astronomy, and one of the ones that's been discussed on the SARA mailing list is looking at options for the way that you collect reference samples. So this is a little bit more advanced than this talk really, but it's just to mention that the standard way we collect reference samples is to collect another sample that is at a slightly different frequency from 1420 megahertz. So that's where you collect hydrogen. If you collect one that's say 3 megahertz offset, either 1423 or 1417, then you'll get close to the same type of signal, but this time there'll be no hydrogen on it. And then you can deduct one from the other and get rid of a lot of that background and that software-defined radio response. Other ways of doing this is you can switch in and out a 50 ohm dummy load or resistor. For those who don't know what dummy load is, basically 50 ohms resistor, and just get a reference from that, which you put the other side of your sawbird closer to the aerial. And this is just a little board that you can get off eBay or Amazon or any other hardware site that sells electronics, only like £5 or £6 each, with a number of relays on them, and you can control those from your computer. They use the HID profile, which is used for controlling automatic lights and things in the house. And Ted has included in his software now the option to switch these in and out to use as reference samples. And then there is a third way for doing reference samples, which is very much under development, so it's not yet readily available, but that uses some people own software-defined radios, some expensive software-defined radios, and have a much larger bandwidth, and then you can use part of the bandwidth as a reference, so you don't have to switch anything in and out and just carry on collecting data. But that's a rather advanced way. So for people just starting, I would use the offset frequency one because it works very easily and you don't need any extra hardware. Okay, where are we? Forget that. There we are. That's me finished. Thank you very much indeed. I'll just pass over to Ted now.
To me, I guess.
Yes,
okay.
please. Yes.
Let's see. I'm supposed to talk about Ezra, so hang on. Let me do some sharing here. Pardon me. I found it.
I know some of you may have questions, but we'll just let Ted do his chat first, and then leave the floor open to any questions or anything that people want to discuss.
So hi everybody, I'm going to talk about Ezra and give you a quick introduction. I kind of think of it as a whirlwind tour, so hold on. Oh, that didn't work. Let's go over here. Let's say, aha, good. Okay, Easy Radio Astronomy is a collection of free PC software tools to help explore radio astronomy. The Ezra programs are still in development, but mostly work well. The open source programs run on Python 3 programming language, on Windows, Linux, and maybe Raspberry Pi. Ezra creates lots of plots for many purposes and may not be useful for your current setup. The main Ezra programs may be divided into two types: planning and data collection with 2 programs, and data analysis and display with 5 programs. Here's a quick introduction to each program, starting with EasyWhen, which is a program which helps with data collection planning. This program tells us when a sky object is visible in the observer's sky and in which direction. The legend at the top right says that the sun is indicated by the letter A in black. This plot represents the sky as we face south. Radio astronomy uses the global time zone standard of UTC, which is often the same as London, England time. At various UTC hours, we see the sun here slowly moving across the observer's sky from east on the left to west on the right. On the left is the sun's sky pointing at UTC hours 16, followed by hours 17 through 22. Likewise, using the red letter B for the sky pointing of 11.4 hours right ascension and plus 3 degrees declination, that moves across the sky from east to west at the indicated UTC hours. Here is a busier plot with several galactic plane longitude pointings, showing the whole above horizon sky, as if lying down with your feet to the south and looking straight up. The EasyCall program is one method for radio power spectra collection into data files. We enter the observatory name and its location on Earth in an Easy Defaults computer file, and then enter the antenna's azimuth and elevation sky pointing on the command line, and collect sky radio spectrum data for days or weeks to display and write to computer files. The Ezra.txt data files are human readable. Here we see the observatory location and name, frequency information, and antenna pointing information at the top of the file, followed by many long lines of timestamp and spectrum values. If you have data from other folks' collecting programs, there are various EasyCall programs to translate that data. And the EasyFix program can help correct an Ezra.txt data file. The EasyCon program studies and displays those .txt data files. The recorded original hydrogen signal may be very weak, and it may be polluted with radio frequency interference, RFI. EasyCon tries to emphasize the hidden galactic hydrogen frequency information. EasyCon can create files for fun 3-dimensional display. EasyCon creates a human-readable summary .ezb file of sky location and power. It has 20 columns of calculated values, 1 line for each sample. EasyCon creates GAL summary files of power spectra along one galactic latitude, typically the plane of the Milky Way. Here's an example drift scan spectrum. EasyCon can optionally create GALAN summary files of spectra along one galactic longitude. They are cross-sections of the Milky Way. Here's an example spectrum from galactic longitude minus 58 degrees. The EasyPlot program uses those .ezb files to study the power values and their daily and yearly variance, and perhaps to help identify RFI for removal. Here are a signal's average values showing a daily cycle of system gain variance, apparently due to outside temperature changes. Here is a histogram showing the range of a signal's data values with a few extreme high values on the right. Here's a multi-day drift scan signal showing the daily cycle is shifted to slightly earlier in time each day. This shows that the sidereal day is about 4 minutes shorter than the solar day. The EasySky program uses those .ezb files to map the recorded power on the radio sky. Here is 1 day of drift scan values with bright yellow on the left for strongest power. Here are many days of drift scans with the antenna at different elevation angles above the horizon. EasySky can interpret the values for the missing data between those drift scans. Here, the stronger power values reveal the galactic plane. The EasyGal program uses those GAL files to map the density of the galactic arms in the galactic plane. After collecting the spectra from many galactic longitude, all in the plane of the galaxy, we can stack them up like slices of bread and begin to see patterns. With some fancy math, we can plot that data differently and start to see spiral arms of hydrogen density, revealing the galactic arms. All of this data is from the plane of the Milky Way, and so has the same galactic latitude coordinate of 0. The EasyGLON program uses those GLON files to map the density of the galactic arms in cross-sections of the galactic plane. Here's the previous plot, but we can plot the data in and out of the screen to create a cross-section at the indicated galactic longitude coordinate of plus 85 degrees. This plot's data came from that coordinate of 85 degrees. This is the cross-section, perpendicular to the plane of the galaxy. And we now see those galactic arms as round yellow and red blobs. Interesting that the blobs gently curve up to the left. The plane of the galaxy is not flat. It is curved like a potato chip. Plotting several cross-section files in 3D gives a more complete view of the galactic arms. And we can combine those plots into a movie as we fly around the galaxy with the sun at the pointy center. And here's where you can learn all about Ezra with links and files and movies and even my email address at the bottom. Send me news of your successes. Thanks. Back to Andy.
Thanks, Ted. That was brilliant. Thank you very much. Well, thank you everybody else for sticking with us, and I hope you found that of some interest. And now I'd like to open the floor to everybody else for any questions or comments or just whatever you'd like to discuss, really. First of all, I'm going to just have a look at the chat, just see what's been written in there. Excuse me a second. Oh, right, okay. Right, okay, so who would like to start us off?
Oh, I would. Tom Matey over here in the state of Oregon in the U.S. I have one of those simple dual mesh dish antennas, but I've been seeing quite a bit of noise on my system over time. Your slide showing dew collection and everything like that got me thinking that the container I have my sawbird filter and a couple of other pieces in there might be contaminated with water dew. Any way to do that without using power?
Whether you can, I believe the standard method is to have an inverted container that's open at the bottom, and you put your sawbird inside it, so that make sure it's sealed at the top, such as a plastic pop bottle, and cut the bottom off.
Okay. Oh, okay. Yeah, because I used supposedly a watertight container, so I don't know if water got inside or not. It's mounted, the antenna's mounted on the roof, so it's kind of hard to get to.
Yeah, so that's what I would suggest. So would you agree with that, Ted? And Andrew, would you agree that that'd be a good idea, having a container that's, maybe Adrian as well, that's just open at the bottom, sealed at the top, so that your cable would go in through the hole at the top, but you'd make sure it was sealed with something like self-emulsifying tape or something like that to keep it clear at the top there. I mean, vitally important to make sure that no water gets into the cable itself. So you want any junctions or connectors must be probably coated with self-emulsifying tape would be the better choice. So that it, because if it gets into the cable, you can just chuck the cable away.
Sure. Okay, thank you. Great presentation.
Can I ask a question? This is Pete from the UK.
Yeah, hi Pete.
Hi. So I think I'm just up the road from you, Andrew. Actually, I'm in Stratford-upon-Avon, right in the middle of the UK. I'm a beginner. This is the first one of these that I've been to, and I really enjoyed the presentations. They were really inspiring.
Oh yeah. Sorry, before you continue, Pete, I've just a message has been put in the chat just to correct what I said. Self-amalgamating tape. We must use the right term for it. It's stuff you can get from Screwfix and elsewhere, where it sort of like turns into a sort of rubbery mass that and stops any water getting into it. Yeah, my apologies for that, Pete.
Self-sealing.
Self-sealing,
we call it over here, so I understand what you're talking about.
Yeah, MD Online makes sure that use the right term. Yeah. So apologies for not using the wrong term. Sorry, Pete. I apologise for interrupting you. But please continue.
So I built my first telescope about 3 months ago. I'm mainly a software guy, so I wrote all the software. I'm brand new to everything else. New to radio, new to soldering, new to electronics. So that's been a very fun learning curve. My first one was it was the Noelec Sawbird and an S-Spy, and I had it in a bottle of Huel, which was then inserted to keep the water out, which was then inserted into a Pringles can covered in foil to keep the radio out. But I've recently upgraded to this box, you can see my LNA in there, and dangling from that is my air spy. And over time, I've been trying to get rid of noise and everything like that. And I've run into this problem that my signal's very weak, and I kind of have been investigating everything, and I brought it down to the fact that I'm using a Wi-Fi dish. So I've got a 1 meter TP-Link Wi-Fi dish, which is 2.4 gigahertz. And I thought maybe it's just not resonant at 1.4 gigahertz. So I took it apart. I took the boom off, took it apart, and inside I found this, which was pretty interesting. It looks like a dipole to me, although I'm not an expert. So I thought that maybe these things are just the wrong length for hydrogen. So what I did was I said, well, can I make a new one that is the right length? So I've made this. You probably can't see it very well, but these are 21 centimeters divided by 4, more or less, and they're made out of brass tubing. And from this bend to here is it 5.25 centimeters. And I don't know whether this is too big a project for a noob like myself to take on, but I recently bought a VNA. Is it a nano VNA to try and tune this to the right level, and it's taking me to, it's a steep learning curve. So I've got 2 questions really for the group. One is when I'm doing this, I'm trying to copy the original design where they've got it's kind of a bend in the copper, and the soldering points are down here instead of being on the actual dipole. They're down here. I don't know if you can see that. So I've replicated that, and I don't know whether it's important where you do the soldering. That's the first thing, because my soldering is just kind of around here. And the second question is this a sensible thing to do? Should I persevere with it, or should I buy one of those new booms from the Discovery chaps that people were talking about recently?
Oh, Andrew, Ted, Adrian, somebody help me out. Is it important how long the ballam is?
Yeah, there's 2 points. This is Adrian, and I live in San Diego, California, so quite a bit of ways from you guys. But yeah, here's 2 points. Okay, first you have 2 things working on that particular aerial, as you would call it, or receiver antenna. First is as you well calculated, the distance, the length of those wires are of course should be at resonant at that 1420 megahertz frequency of the hydrogen line, and so you're doing that just absolutely correctly. The second thing is this other property of antennas that's called impedance, and so each antenna has its own characteristic impedance. But all the systems, for example, the coax that you use for sending the signal down to your SDR and so forth, has a characteristic impedance, which is usually stated as 50 ohms for use in radio astronomy. And so that dipole that you're creating doesn't necessarily have a 50 ohm impedance. So those 2 lengths that are kind of adjacent to each other and running down the cable is a way that you can use to adjust whatever the impedance of that dipole is down to approximately the 50 ohms. So there is an importance as far as where that point is. Now you're doing it just absolutely perfectly correctly. Using your VNA, if you scan that antenna with your VNA, you'll see that there'll be different responses on it depending on 2 things. One of them is the resonance of the antenna, which is determined by the length of the 2 dipole elements, and then the second thing will be the impedance plot, and that you can also then adjust by finding the point along those lengths coming down that gives you the best closest match to 50 ohms, and that's usually that circular graph that's called a Smith chart that the VNA provides for you. So those are the 2 important things then to pay attention to when you're generating, and you're doing absolutely correctly by trying to adjust the length of those 2 dipoles so that's more closely approximates the the hydrogen line rather than the 2.4 gigahertz Wi-Fi signal. So anyway, those are the two things that I would recommend. Just use your VNA and then match for those 2 points, the resonance from the two dipole, and then using the Smith chart output from your VNA, then the impedance match to make it closer to 50 ohms as you possibly can. And those are the only two things you can do for that. And then, of course, then just find the correct focal point for the antenna. I understand there's some confusion on some of those wire grid antennas as to where the exact focal point is from the way that they're sent out and the actual focal point for them. So that's a different situation. But as far as what you're constructing there, you're doing it just exactly what you should be doing. So I hope that helps. I don't know if that does, but
that's great.
Anyway,
yeah, thanks a lot, Adrian. Nice one.
So I just make a comment on that. Firstly, Adrian, the mismatch in the length of the boom was specifically about that Alex had picked up on the Newelec 1.42 gigahertz dish and boom. I don't think it is on any of the other ones. So his 2.4 gigahertz Wi-Fi antenna, it quite probably is correct in terms of the length of the boom. I think you've done absolutely the right thing getting a nano VNA. They're absolutely brilliant. Adrian is extremely knowledgeable and far more knowledgeable than I am. I've got to say that up front. Much more knowledgeable than I am. In our hydrogen line meetings, he's one of our resident experts to help the rest of us out. Having said that, he understands Smith charts. If you get a Smith chart, never seen one before, then you'll be the same situation as me, which is you won't know what it means at all, and I don't. I have no idea what the things means. I just looked up a little bit of information. It's just worth saying that if you understood what he was talking about there at all. So he was saying there is the resistance and also the impedance, which is like a sort of resistance you get when things change, when the signal strength changes very rapidly in a sort of alternating current, which is what you get basically with a radio frequency. So the impedance of a halfway dipole at 1420 megahertz is 73 ohms natively. So it's not so far off what you actually that 50 ohms that Adrian's talking about on the cable. In fact, in reality, the real world range is often a bit less than that, from 65 to 70 ohms. So it might even be better than actually the 73 ohms that's stated there. And on the whole, when you are receiving things, I'm going to go out on a limb and say it isn't so important. If you were trying to transmit and sending any significant current down an aerial or antenna, perhaps we should call them antenna really, for the sake of American cousins, then it's much more important whether you've got the impedance matching. Okay, usually something called the VSWR, which you pick up on your nano VNA there. Usually, if you get somewhere around 1.5 to 1, you're doing really well. Many people would say that less than 2 to 1 is doing pretty well, but less than 1.5 to 1 is remarkable, really. And the sort of difference that you would get between that sort of 73 ohms and the 50 ohms could well leave you well within that 1.5 to 1 on your VSWR. So don't get yourself too worried about that. There are various ways that you can fix it if you want to. Just for the sake of anybody here who is interested, it's supposed to be a beginner thing. If you're interested, you could have something called a folded dipole, which has an impedance about 300 ohms with a 4 to 1 balun, or you can have a quarter wave matching section, which is probably what that thing is that you're pointing to on your dipole there. So once you change the length of the two arms, your dipole, then your quarter wave matching section is going to be wrong, because it'll be the wrong wavelength. So you're better off with a straight piece of coax that goes up. The outside is soldered to one piece of wire. The inside is soldered to another piece of wire, and then they go to that T that you've got, as you saw on there, but basically soldered at the top, and just go one in one direction, one in the other, and cut them to length. And if you want to do it really well, you would use your nano VNA and slowly cut them down until you get just so. and get them tuned in.
So cutting these down, well, that affects the frequency at which it resonates. I understand, but how can I modify the number of ohms that it's operating at?
Well, as I say, it's quite complicated. The easiest way, in all honesty, if you're making it yourself, is not to bother. So if you put your aerial up again, so put your waveguide up there again, your dipole, hold it up. Okay, I've got you for what it's worth. I've actually got you on the screen. I've set you up to full screen for the sake of the video.
All right.
So you would, in essence, remove the plastic bit on the right hand side. Just get rid of it. That's the matching quarter wave section. So you get rid of that, and then you would just solder straight up at the top, one on the left, one on the right. One would be on the.
So the soldering point would be right at the.
Yeah. So inside there,
so
you've got the
soldering
coax coming up, and as the coax comes up, so at some point there's coax, and you've got the outside of the coax and the inside of the coax. So the inside goes to one side, the outside goes to the other side. You make sure they don't touch each other. Right.
With some of that self-amalgamating tape that you were talking about earlier.
Well, it depends what you've got it inside, really. I mean, that is just where if you've got a junction where stuff might go into a coax, and if you've got cable connected from out to other cable that goes outside down to a run to a computer or something, you want to make sure that's covered and it's not going to get water into it. But I'm very happy to have meetings outside of here, and I know that a lot of the guys that are on the call here at the moment will also be very happy to do that, to give extra support to anybody that wants to go through it. Somebody has also put on the chat, I saw it come up but didn't get a chance to see the name, see who it was.
That was me.
Yeah, tell me. Yeah. Oh, you put some how to use a nano VNA to test it. Yeah, I mean, if people want it, we could also run a session on actually testing antenna using a nano VNA. So that could be another session that we run. It can be done, or you can buy a separate feed, or many people do it. I was today. You can see it. This is a cantenna, slightly posher cantenna, made from a piece of aluminium flue pipe for stoves, and it has a cap on the end of it, and a chassis connector, N-type chassis connector on the side, and this is one that I've been making. As you can see, it's got a probe in there, and actually this has got a tunable probe on it. So I've made it so that I can, without chopping it, I can twist a little screw on the inside. And I was doing it today, and I used an nano VNA to tune that, and it was quite remarkable how, when I got it into just the right spot, the performance just shot right up. And I moved it slightly more, and it disappeared again. So, but I mean, there are different ways of doing it. For what it's worth, here's another piece of aluminium flue pipe, but this time it's got cardboard and silver foil around the outside of it, and this is what's called a choke. So this is one way of actually improving performance on a dish. One of the problems with dishes is that they tend to pick up reflections of radio waves that bounce off the ground or bounce off trees or the house or whatever, and in this particular case you can reduce that by having this choke on the outside, which will cut extraneous waves out. So there are all sorts of things that can be done to improve signal, but in the first instance, just keeping it simple is probably the best way to go, just to get things working, unless you're already part of the way there and want to improve what you've got.
Quick question about your cantenna. That probe, is that a monopole? So it's just like a single piece of copper sticking in, is it?
Yeah, so I've got my cantenna box here. If you join the SARA mailing list, then you will find this is an absolute can of worms about how you should make these things. But still, So one of those is a is an N-type chassis connector. It doesn't necessarily have to be N-type. I use N-types because they're big and bulky and strong. And I'm the idiot that's walked into French doors and bent dew shields on telescopes before now. I've dropped my friend's Ethos eyepiece on the floor, and his telescope also fell off my equatorial platform when it moved to one side. So anything which is more robust when I'm using it is well worth it. So I tend to buy the biggest, robustest ones I can get. So the point about it is you drill a hole in the side of your can, and then that's got 4 little holes there, and you drill a hole in those and stick some little nuts and bolts on them, and you can hold that in firmly. And on the inside you've got a single connector coming out, and I will show you exactly what I used the first time to create my monopole probe on the inside. This was really high tech, this. I've got a whole box of them here. I can sell you one if you want one. There's one of the special Andrew Thornett monopole probe devices. It's called a paper clip, and I just straightened it out and chopped off an irrelevant amount and soldered it on the inside. I'm getting a bit posher these days.
Amazing.
So I've now bought myself some of these things, which are copper tubes about an 1/8 inch wide. I don't know how much difference it will make, but the paperclip worked. That's all I can say. You got to get the length right.
Thanks. Thanks, Lucky Help.
That's not easy to solder steel.
To be honest, I found that much easier to solder than I did the copper tubing earlier today, because it was.
Why not just a piece of single strand copper wire out of some cable?
Yeah, I've done those as well. They work as well.
Solder,
Yeah,
shape it.
yes, some mains cable. That's nice and strong. You can get out a bit out of the inside of one of those.
There's a lot of people talk about 3mm diameter brass tubing, and I don't understand why so much.
Right. Okay. So, wait a minute.
Well, the 3mm fits in that connector that he was showing
Okay.
quite nicely.
Okay.
Right. This will demonstrate the answer to your question. Indirectly, the question you're really asking, which is, does width matter? This is a professionally made coaxial to waveguide adapter, WR650, which is the right wavelength, the right size for hydrogen line. That's what I'm going to use at the bottom of the horn I'm making. But what I'm going to point out is the monopole probe that's on the inside of that, with its great lumpy bit on the end.
Yeah.
So the reason they've done that is because it broadens the wavelength that it picks up, or the frequency it picks up. Makes it more flexible. So
So you get a better bandwidth.
yes, yeah. Well, you can be a wider range of frequencies that you can pick up. So I mean, I'm not quite sure other aspects of performance. I don't know, Ted, Andrew, Adrian, did you know if a narrower probe actually leads to better performance in some way? I suppose it probably does.
Well, it just sharpens the peak. So, like, again, if you were, say, tuning that with the with your VNA, you'd get a sharper peak with the narrower monopole, or half the dipole. And so the width here would just kind of broaden out the peak that you would see. So that's what Andrew's referring to. That it gives you a little bit more bandwidth. So it's not as sharp response, and so you know, it's not a huge amount, but it does broaden it a little bit. So again, as was presented earlier, with the Doppler shift of the signal and so forth, you would want to have a little bit of a broader response. rather than just something super narrow right at 1420. So that might reduce your signal a little bit. So it's not a hugely important parameter, but that's the explanation.
I mean, in terms of bandwidth that you require, the RTL SDR blog receivers quite happily cover the required amount, don't they, Ted? I mean, we only need about, what would you say, about a 1,000 hertz, something like that, or what do you think need? Oh, 2.4, like 2.4 megahertz, Ted just said, yeah. I mean, that's what the RTL SDR blogs offer. And usually there's enough spare on the side that you could use that, or at least Alex Pettit points out you could use that for sort of calibration purposes.
So you've got to make sure the filter's got that bandwidth there, then.
Who was that?
Yes.
Sorry, Rob.
Okay. The filter's quite happy. The bandwidth on the filters, I think it's plus or minus 30. Plus or minus 30 megahertz, I think. Actually,
Megahertz, yeah, right, yeah.
Yeah.
Okay.
I mean, I've got a.
I'm used to.
Sorry.
I'm used to 23 centimeters contesting, where our bandwidth on our filters is very tight.
Yeah.
So something wider is better.
Well, I mean, it's interesting. You don't need it to be that narrow. I've got a cavity filter that I got from China that gives incredibly narrow bandwidth of plus or minus 2 megahertz. I mean,
What we have is hydrogen that moves towards us and away from us. So we got this Doppler shift stuff to worry about. And of course, it's fun to study it too. And that's what is actually taking up the bandwidth. So you got to be able to accept it coming and going. And some of that, of course, is just the Earth's motion. And we can't change that part. So we got to be able to handle at least a megahertz. And it's more fun to have some frequencies that aren't being changed by hydrogen, non-hydrogen frequencies. So we make the bandwidth a little bit bigger. It's remarkable how well the RTL SDR is just about the right size. You know, you can deal with it pretty nicely.
Okay, good, thank you.
Thanks, Ted.
I suppose. Go ahead.
Yeah,
Sorry.
no, you go. I just said thanks, Ted. Carry on, Tom.
Oh, I was going to say, it just depends on how much RFI you got in your local area, too. If you got, for whatever reason, you got RFI that's next to 21 centimeters, you may want to use the narrower bandwidth just to help project that.
Yeah.
You're trying to reduce the noise coming into the system, you're saying?
Yeah,
Yeah, we don't want to overload the front end with
absolutely.
powerful signals. I agree, and that's what filtering is useful for here.
The other thing to bear in mind is if you're using offset reference samples, you need to be able to accommodate those frequencies as well.
Okay.
But as
That's effectively frequency switching, is that right?
yes, yeah. Do you want to talk a little bit more about
Going
that,
back-
Ted? Explain how Easy Rate Astronomy does that.
There are two ways that Ezra studies it anyway. What we're trying to do is somehow emphasize the hydrogen signal. It's so weak, how do you pull it out of all that noise stuff? One method is simply to compare the middle of the frequency band that we're looking at that has hydrogen to the outer edges that don't have hydrogen. And if there's big noises changing our whole environment, we can kind of study it with that outer edges. So that's kind of a baseline approach. We can accentuate the hydrogen, or at least make it smoother at least, by studying that baseline on the outside that doesn't have hydrogen. Okay, so that's one frequency. But wouldn't it be nice just to compare this shape of spectrum response to another frequency that doesn't have hydrogen and just compare to that? And so that's the concept where Ezra changes the frequency for you from here to there, from here to there, from here to there, and able to compare your sky signal from with hydrogen to something that came through the same system, has the same frequency response and all, that doesn't have hydrogen. And so that's the concept of a reference sample. And that's the frequency switching that we just spoke of. Now, another way to do it is simply somehow put a resistor in there and compare to a resistor, or compare to the sky and compare to the resistor. Now, I keep saying about alternating here because I found that over time the environment changes, and so it'd be good to have a recent reference to compare to. So often the default Ezra will compare to hydrogen versus not hydrogen and alternate back and forth, sample by sample, so that you have a recent reference sample. That's the quick introduction to what Ezra does for emphasizing. I hope that's helpful.
Yeah, no, I was asking because I read it. Frequency switching is how the original the horn of plenty was used. It was essential for getting the stability that they needed.
Well, that's neat. I haven't read that much. That's cool to find out.
Yeah,
I happen to fall down the same track. That's good. I saw it in somebody else's code.
Right. Yeah, I mean, I used to work in a totally different science where, given the shape that you've got, you could try something called baselining, where you choose an area of the curve each side of your area of interest and try to model the line shape you would get in the absence of any hydrogen signal.
Okay, that's the first method I was describing.
Right.
In my Ezra, I call it Ant B, just because it's the signal from above from the antenna, compared to some baseline, and that's what the B was for.
Great. You know, a lot of cans have corrugated sides or corrugated bottoms. Do they ruin it, do you think?
I think you'd have a hard time measuring the difference.
Right.
Yeah, that issue came up recently, as in last week, because, just to show you, that can that I was making there, that's the cap that I got to put on the bottom, which is, so they're sold to go on the top of flues outside so that you can stop sort of, I don't know, leaves and things getting into them, dirt getting into them. So of course, that's going to decrease the size a little bit on the inside of the can. And the conclusion was on the SARA mailing list that it probably made very little difference. And I've got to say, when I was trying tuning it today with the Nano VNA, it didn't seem to make much difference. But obviously the real world test outside on the telescope is going to what's matter. And I can come back to you and let you know, but I think probably not is the answer. I do think that the length of the probe matters.
You could fine-tune the distance.
Well, again, that if you read stuff online, that's supposed to be really important. The distance from the connector as it goes into the connect to the probe as it goes into the cantenna, and the back of the cantenna is supposed to be important. But Andrew, perhaps you want to briefly mention the research that you did on that you presented to us recently.
Yeah, well, I've been playing around with 3D printed waveguides and looking at the difference in putting the position of the probe, so the distance from the bottom of the waveguide to the point where the monopole goes in, and then the length of the monopole. And basically, there's not a huge amount of difference. You can make large variations from 40 mil right up to 100 mil from the base, and I use probe lengths from 42 mil up to 56 mil. And when you get down near the 40 mil or up near the 100 mil, the differences are larger, but across the middle of the range, there isn't a huge amount of difference in the level of signal that you detect. So for the hydrogen, I don't think there's a huge difference.
So you'd say 60 millimeters is a good place?
Yeah, 60, 70, 80, you know, it's not going to make a huge amount of difference.
This is from the back of the antenna to the probe, is what you're talking about. Yeah. So at Astrapellier they use, I think it is 88 millimeters. No, they use 92 or 93 millimeters. So 92 or 93 millimeters, and that seems roughly about right. This is for 150 millimeter wide antenna, because it does change depending on the size of the antenna, and you can get antenna calculators online. So although Andrew's research seems to suggest that it doesn't matter too much, I suppose there's always the caveat that might be dependent on the material that he's 3D printed his can out of. It's just possible. So I think it might be worth, if it doesn't matter, then it doesn't matter, but it'd be worth going with more standard measurements. Using the tunable probe today, I would certainly say the nano VNA response seemed to change quite rapidly at one point, and rapidly improved and rapidly dropped off again. So personally, I think the length of the monopole probably does matter. But again, there's always the caveat, it might depend on the material, etc. So what is it, Tom, you want to say?
Pardon me here, my Frankenstein monster antenna.
2 coffee cans.
2 coffee tins, yeah. So monopole inside, only reason why I got copper on the sides is because I have aluminum sheeting putting the 2 cans together, and I thought, well, the electric shielding can't hurt. So this is my first antenna. It actually worked very, very well. So, you know, for all the bolts and nuts and everything else I got in this thing, it's surprisingly robust.
Well done. Very well done.
Yeah.
And do
that's
you
that's a good,
sorry?
good length too. How long is that?
How long is this? I used one of the online calculators. This is 17 and a half millimeters, or centimeters, sorry. Look at the wrong measurements here. 17 centimeters. So 17 by the narrow opening is just over about 13 and a half centimeters.
So that's the diameter, is it?
This can is simply a waveguide. And as long as it's nice and conductive, it could be very long, and finally you're just you're pulling the signal out of the waveguide at the very end. And that's why the distance to the shorted end at the end of the tube is the important part. And Andy, in the Sarah talk we had, it was suggested that, it's not terribly sensitive, that distance to the back end, to the short at the end of the waveguide, the cap on the end, because you're just trying to get the peak of the sine wave for the strongest signal at your probe. And if you move a little bit to the left, a little bit to the right of the peak of the sine wave, you're about the same value. The slope is pretty flat up at the top. And so this, by physics, it starts to make some sense. If I may, let's go back to Brandon's question on the chat, though. Brandon, you say you got a Noelec Sawbird. I hope it's for the right frequency, 1420. And you got some kind of RTL SDR. Sounds great. But you were a little worried about this talk about the boom of the Noelec gigahertz antenna. And Andy, the length of the boom, Alex did some study and he thought it was like the wrong length or something like that. But the problem is, it also works. So you're just fine-tuning your antenna. Did I get that right, Andy?
I don't know whether the 1.42 gigahertz Noelec boom works.
Okay.
I haven't tested it.
That it could be improved that they kind of cheated and used some convenient part or something like that. But I think you'll find that it works well enough to receive hydrogen from the sky.
Well, one point is that whatever the focal point is, it's irrelevant of the frequency. So if they got it right at 2.4, it's right at 1420, and vice versa. So again, the frequency has nothing to do with the focal point. So just thought I'd mention that. So you don't have to worry about the frequency of the antenna itself, because the focal point will remain the same for all frequencies.
Okay. Yeah, very good.
Awesome. Thanks, y'all.
In the beginning, I think it's more fun to play with some data rather than keep tuning your antenna.
Yeah.
Good luck.
Yeah.
Yes, sir. Thank you.
Yeah, I think it's just worth saying this is a project that can be successfully achieved just using a CAN, or for that matter, as the SKAO outreach team show, with a load of inflated balloons and some silver foil stuck on the inside. It's possible to way overdo it and get too worried about it. They can get a bunch of school kids in an afternoon to produce a working hydrogen line antenna and a working hydrogen line receiver, which they put in some little old sweet box with a Newelec Sawbird and a cheap SDR attached to it. So if they can do it, anyone can do it, really. If I can do it, anyone can do it, definitely. If anybody would like any further help, then please do contact me, and I'll be very happy to get separate video sessions if you would like them, and we can do. I'm very happy to do that. I'm always happy to see other people's kit and see what they're doing as well. Even if you just want to meet up and have a chat, that's absolutely fine. On whatever topic to do with radio astronomy. What else? If you've got any ideas for some good subjects for a follow-up meeting from this, then please do again drop me a message, and if there's enough interest, then I will look to set up a separate meeting to follow this up with whatever topics are of interest to people. Is there anything else before we finish? Well, thank you very much indeed.
Just a quick one.
Yeah, go for it.
No one's. Well, I think you mentioned Yagis right at the beginning of the talk. Does anyone use Yagis, or is everyone using horn antennas and dishes?
So they're worth mentioning, very much worth mentioning, in as much as I've mentioned Alex Pettit several times and his H-Line 3D project. If you actually type in Alex Pettit, Pettit, H-Line 3D, or Alex Pettit GitHub, or GitHub H-Line 3D, then you'll come up with a GitHub link on your favourite search engine, which takes you to his H-Line 3D project, and a number of documents on PDF documents on there, including one about design of kit that he's put together. And one of the things that he's produced is a design for a Yagi antenna, and I think you may still be able to order them from him, which they perform incredibly well. I've got one of his Yagis, and he's attempted to produce a small antenna which is easily portable, will work on things like patios or people's balconies if they live in blocks of flat, and it's just an excellent piece of kit.
Just like an optical telescope, a big telescope collects more photons from the sky. So if you can fit it, a dish works nicely if you can make it work. But if it's great that a Yagi is smaller and it just takes up less space, maybe you can take it down and put it in your shed or whatever. I have posted in the chat my comments about a $20 antenna, which is just made out of copper wire stuck on a PVC pipe. I prove in the video that it works and does things and sees galactic arms and stuff. I say that bigger antennas work better, yeah, but it works. We've also had great fun lately with disc antennas, and Alex has taken it to great efforts to design it and make it bigger and longer and more sensitive, which is great. Even shorter ones work fine too. So yes, Yagis are quite possible. Horns are pretty darn easy, even with aluminum foil, silver foils, you might say. And even just a simple dipole will receive galactic hydrogen if it's an acquired environment. Give it a try. In Ezra, there's hardware number one of the PDFs attached, even up there on the web, and you can see several different kinds of antennas. Give it a try.
Thanks.
Yeah, I didn't mention Yagis earlier on in my talk, as much as anything, because it's a slight step up in sort of manufacturing requirements for somebody who's trying to start off and perhaps has never done one of these things before. But conceptually, they're not difficult to make, and as Ted says, he's actually himself created a design for one for only about $20 or so, made with some PVC pipe and some of the bits of wire and stuff stuck on the side of it, which he's very effectively used. I think he's used as an interferometer as well. Two or three of those working together.
I only ask because I've got 4 2-meter long Yagis in my shed, but they're tuned for 1296 megahertz, so they'll be no good for hydrogen line.
Yeah, well, that's the problem with any aerials or antennae, isn't it? They need to be tuned for the frequency that you're using them for. That's the difficulty.
Is there any reason why a small dish couldn't be put in the loft of a house?
You have a lot of loss just because of the roof above you.
You do? Okay.
Yeah, I'm thinking. I wanted to comment that, remember that the dish that Sarah sells as a scope in a box is for the wrong frequency. It's for 2.4 gigahertz, and yet it works remarkably well. It kind of surprised everybody. So I would try the 1296 Yagis and see what they do.
I've got a phasing array for them, so I could somehow get them back up in the air.
I would do one at a time to start with. That's all.
Yeah. They haven't been out of the box for a while.
I mean, I'd agree with that.
COVID.
I would agree with that. Just try one on its own.
Yeah.
Yeah. I'm sure you'll get it working, actually. It'll be very interesting to hear what you managed to do with those. Or I'd love to hear from anybody else here if you are trying to do any radio astronomy work, and let me know what you're doing and how well you're getting on. And as I say, if you're having any issues, we'll try and provide some help.
Time to try some things. Thanks ever so much, Andrew and Ted and the others for your contributions. It's been brilliant.
Right. Just a couple of queries in the... Thanks very much for that. But it's a couple of queries that are in the chat just to finish off. Firstly, somebody asked for a bit more information about the potential problems with the 1.42 gigahertz Newelec dish. I think we have addressed that a bit more, but perhaps just to summarise. So Alex Pettit, who is a member of SARA, has been doing some analysis, and he has concluded that the boom, the stalk in the middle, is too long on the Newelec 1.42 gigahertz dish and feed, which is one that's sold specifically at that particular frequency. As Ted said, it may well be that it still works quite effectively. That's the strange thing about hydrogen line. The signals we describe them as being weak, but actually in the radio astronomy world, they are still relatively strong compared to some other signals that you might be trying to pick up. So maybe that's the reason that they're sold that way, because they still work. But if you've got one, just give it a try. But if you haven't got one, it might be worth considering that as an issue, possibly, and considering something separate. Having said that, the 2.4 gigahertz dish and feed, which is designed for Wi-Fi, which is sold in the scope in the box package, I have actually spoken to the chap that organises that, and I just said to him, should we now be moving over to a specifically tuned antenna, as a few are now available? And he said, well, there's no real point, because the 2.4 gigahertz one works, and they're so readily available all around the world. So that's his attitude to that. So, it's a good point. The second thing was that is a question from Rob here. Any other interesting targets, hydrogen apart from the spiral arms? The problem here, Rob, is that we've had a lot of discussion again about this in the Hydrogen Line group. The issue is the aerials that we're using. You can pick up other targets using this kit. Basically, something like a hydrogen source within the Milky Way, rather than just larger clouds, which is where the Milky Way arms come from. The problem is that at the sort of resolution that we get on our graphs, you just have one single pixel. So you have a map with a single bright pixel in it if you manage to take it further, which is all you would get if you improved the quality of the signal that you were getting. So it doesn't really achieve anything very much. You need a much bigger dish to be able to not only pick up more signal, more, so that you've got more integrated data to get you the fainter signals, but you also need the bigger dish to give you the bigger resolution, or the better resolution, so that you can get more detail with those sort of focal sources that you're looking at. Is that correct, Adrian?
Not for this talk. The interferometry, but definitely not for this talk.
Oh yes, this is not about interferometry. That's the other option. Go down that route, get two dishes, and try to achieve that.
Yeah.
Best of luck. For anybody who is interested in interferometry, there are, with small dishes, you can pick up about 5 sources in the Milky Way with an interferometer, and you basically say, oh yes, I picked that one up, 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 I picked that one up. That's great, what do I do next? Because that's about as much as you get out of it. Sorry, Adrian, you wanted to say something?
Yeah, I'd like to point out, and this is just kind of a plug, okay? So as Andrew, and he's a member, and as he pointed out earlier, if you become a member of the Society for Amateur Radio Astronomy, and the membership price is quite reasonable, I think it's only like $20 US or something like that, you do have access to a 20-meter professional radio telescope at Greenbank, West Virginia, so you don't need any equipment. If you join Sarah, you can actually use this gigantic radio telescope for free, and gosh, you can do all kinds of astronomical objects and other targets. Mentioning other targets, there's, for example, astronomical masers that you can actually observe. These are discrete signals that come out from certain molecules, like the hydroxyl radical, for example. They're masers that produce radio frequency signals. There are different frequencies, but you're capable to observe these with the Greenbank radio telescope. So again, just a plug for Sarah. If you're not a member, please join, and then request access for the radio telescope. And Andrew's quite adept. He's used it for some tremendous kind of work, even looking at the hydrogen line from other galaxies besides just our own Milky Way. So again, just a plug for Sarah, and just look into it if you're really interested and don't necessarily have the space, or you live in an apartment, don't have the room for antennas, and maybe neighbors won't let you put stuff in your backyard or whatever. That's one other option. Anyway, just thought I'd point that out.
Yeah. So I mentioned Jason Burnfield earlier on, who is works at the VLA as one of their technicians, and he and I together have used the 20-meter scope, Skynet scope at Greenbank through the SARA account, and we have plotted that galactic curve line, that smoking gun for dark matter talked about, in galaxies outside the Milky Way, in other galaxies such as M31. We've also mapped M31, mapped M33, We've mapped the Leo triplet and also M81 and M82 in the area around them, trying to pick up the streams of hydrogen that go, or the clouds of hydrogen between the galaxies, as well as the galaxies themselves, and picks up some other areas where there are some other smaller galaxies, which is quite interesting to find out where you get some galaxies which optically look brighter but actually seem to have less hydrogen signal when we map it. And other places there were some galaxies which don't look as bright and yet seem to produce a stronger signal when we start the mapping exercise. So it's there's a lot of interesting stuff that you can do, especially when you get to that size of telescope, and it's amazing to have that facility. Now, Adrian has mentioned the fact, again, you have written in the chat there, as you just said, Adrian, that there are other targets such as astronomical masers, like the OH masers. So it's worth saying that there is a member, Edward Moll, in the SARA group, who I think he's based in Germany, I believe, who actually successfully detects masers using a 1 meter dish. And it's a standard 1 meter offset satellite dish. And he actually mounts that on a HEQ5 Pro mount. So again, this is outside what this group is really about tonight, but just for your interest. He mounts it on that and used the HEQ5 Pro to point it at an area where there's a maser, and it has successfully recorded masers using that setup. The pulsars are being detected by people with 3 meter dishes, but again you need to have some pointing accuracy with that. But this is starting to get into rather advanced amateur radio astronomy, and it's just perhaps ideas that once you get this one under your belt you might want to expand to.
I wanted to point out a detail that's just more for correctness rather than any other, doesn't change anything that's been said today. But we've been referring to picking up the hydrogen signal. And I just wanted to point out that what you're actually detecting is the hydrogen line signal from, not from molecular hydrogen. Of course, you know that hydrogen exists as a molecule, as H2. And so what we're actually receiving is the signal from atomic hydrogen. So in space, because of the sparseness of in the vacuum, you can have single atoms of hydrogen that exist by themselves. And so the signal that's being emitted is actually a signal that's peculiar to these single atoms of hydrogen, where you have essentially an energy shift between the so-called spin of the proton and electron in the atom of hydrogen. And so depending on the orientation of the spins, if they flip from one either parallel or anti-parallel direction, you get this hydrogen line emission. So when we're referring to hydrogen, we're actually referring to atomic hydrogen. And unfortunately, molecular hydrogen, which also exists in space, does not emit a radio signal. It pretty much has to be detected by other means. And of course, it's optically, you can detect it in absorption lines and so forth. But so what we're referring to is the atomic hydrogen emission at 21 centimeters. I just thought I'd want to point that out just for accuracy and not to change anything that's been said today.
No, thank you, Adrian. That's really good. Thank you. Okay, so
when two hydrogen atoms meet, they can't combine into a hydrogen molecule unless there's a third particle to help them. There's nowhere for the energy to go when the two hydrogen atoms combine, so they just separate again. And so when you've got very low pressure hydrogen atoms, it's very little chance of them combining to make molecular hydrogen. And conversely, probably when you've got enough density to combine them into hydrogen, molecular hydrogen, it's probably dense enough to form a star eventually. So I think there is a lot more atomic hydrogen than there is molecular hydrogen until you get down to planets.
Oh, that's interesting.
Which is good for us.
Yeah, that's absolutely correct. So you're absolutely correct there. I just thought I'd pointed out the
it's
origin
good.
of the signal, where it's coming from, and
yeah.
and so. But you're absolutely correct. And when you start forming molecular gas clouds that are beginning to collapse due to gravitational collapse and forming beginnings to the formation of stars and so forth, then that's when you start getting some of these other molecules. Again, as I referred to earlier, even these masers that I referred to, these are from regions of the sky where you do have these higher concentrations of other molecules like carbon monoxide and hydroxyl radicals and methanol and other molecules that then can produce these maser signals. But you're absolutely correct. The vast majority is atomic hydrogen in space. So that is correct.
As it was, soon after the Big Bang. Yeah.
Now, Ted wants to ask Ted a question. Ted, we point our antennas towards the center of the galaxy. That's where all the stuff should be. We should see really strong signals. But actually, we don't see much galactic hydrogen at 1420. Is that because there's too much pressure and it's not atomic hydrogen anymore? What's the reason? Or is there dust or what?
So I believe near the center of the galaxy, the star density is much higher and the gas has all been cleared out.
Well, you're saying it's blown away the hydrogen. But
no, well, some will be blown away,
stars.
yeah. But otherwise it's in the stars.
You would think that there's a envelope around the center, that a wrapping around it that would have hydrogen. It's just puzzling why when we look at the galactic center, we don't see 1420 emission.
Yeah. Well, the density of stars in the galactic center is more than 1,000 times higher, I believe.
Oh yeah.
So.
And good thing, otherwise we'd all fly away. But yeah.
Well, it's a funny thing. Some galaxies don't have a central bulge. Most do, but spiral galaxies.
Wow. Okay.
There are some which don't have one.
Yeah, a good example of that, for example, are the like Magellanic Clouds. Some of these smaller galaxies do not have central bulges or even central massive black holes. So
no, there's still a lot we don't understand about the structure of galaxies. Even the one we live in.
There's even some galaxies that are supposedly lacking any significant amount of so-called dark matter, which is almost unbelievable. But so if you can think of the variation, it's probably out there.
Yes. I was recently looking at the classification of galaxies, and where there used to be 4 or 5, there's it's over 20 now, I think.
We even have these new things that the Webb telescope is now calling little red dots.
Yeah, and it's one of my pets is about so they're finding brown dwarf stars or things that are bigger than Jupiter, but not big enough to fuse hydrogen. Some of them can fuse deuterium. There's some which can't even do that, but they can fuse lithium apparently. And so they keep warm for a bit, but then they cool down. And so, unlike other stars, these brown dwarfs actually, their temperature and colour depends on how old they are. And I suspect we underestimate how many of those there are out there. These space telescopes are good. Did somebody say something about the spiral arms, where the stars are and where the dust is? I mean, which are you looking at with the hydrogen line? Are you looking at the bright spirals or the dark spirals?
Well, that's a good question.
I don't think dust blocks the hydrogen emission too much.
No.
So
where is the hydrogen?
So you're basically looking at where the hydrogen atomic concentration is the highest, which is in the spiral arms.
Mm-hmm. So in the bright spirals.
We think the galactic hydrogen emissions coming from the same place where we see stars.
Yeah.
Yeah.
That makes sense because the nomenclature of the spiral arms. Yeah.
And as you said, where the gas is where you form the stars. So it's kind of like the chicken and the egg.
Yeah, true.
Which comes first? So the hydrogen, it has to be there in order to collapse to form stars. And so, ergo, that's where you're going to find the hydrogen, where the stars are.
Yeah.
Is that a name of a movie? Where the stars are?
Are you talking about Hollywood stars?
No, it's just stars in general. I was making a dumb joke. Yeah, my astronomy club over here, we just recently bought some property. We just installed a 4-meter radio telescope, so it's still in development. And hopefully this coming summer they'll get it up and running. And we're hoping to do remote. This is in Oregon. This is on the western side of the U.S. So, and it's out in the desert. So it's a ways away from everything.
It's radio quiet. Brilliant.
Yeah.
So is Eastern Oregon? What part of Oregon?
Central Oregon, just outside of Prineville, just south of Prineville.
Okay.
Yeah. If you know where the Oregon Star Party is, it's just west of there. But it's they got the property cheap, but it's I think it's about an acre in size, so they're in the middle of developing it. It's all shut down because. Go ahead.
Will this be a steerable radio telescope or more fixed?
Yeah, it's going to be steerable, and they're working on remote access as well. Sort of has to be a remote access.
And this is a built-up telescope, or is this like a surplus telescope?
Yeah, it was a surplus telescope. I want to say C-band. That's right. The old big dishes they used to have. They got one for free, just haul it away, and so they went through and had the local university senior project. Electrical engineering department as a senior project that went through and reconfigured it for astronomical use. So it's going to be multispectral.
What's the name of the group?
The astronomy club is Rose City Astronomers.
Rose City.
For Portland, Oregon.
Rose City
Astronomers.
Sounds good.
Yeah.
Can I just can I interrupt just a second? I think that as far as the formal part of the session this evening is concerned with our discussion, I think I don't want to halt these discussions. But I think what I'm going to do is call formally end the session that's being recorded. And say thank you very much for taking part. And as I say, if you do have any further any ideas for further meetings, please don't hesitate to let me know. Also, in addition, if you would like any help, then please don't hesitate to contact me, which you can get hold of me if you're watching the video and you don't know how to get hold of me. If you get through the BAA Radio Astronomy group, they will put you in contact with me. Or alternatively, you can go on to my website, which is www.astronomy.me.uk, and just use the contact us form on there. So I'm going to call a halt and finish the video now and say thank you. But having said that, you guys don't need to leave. You're more than welcome to carry on talking.